The Internet is a cluster of millions of interconnected networks. Networks that form the Internet are arranged in three levels. The first level is the Internet core, which is made up of the global backbone networks and transit networks. These are run by transit operators and carry a significant share of international IP traffic. Transit networks are interconnected by Global Internet Exchange, GIX. The second level includes a large number of national or regional networks. On the next level, towards the end user, we find networks which have only one single upward link to the national or regional networks. At this level, we find the third category of operators, Internet Service Providers, or ISPs. An ISP provides end users with the Internet access. Often, these networks are local or cover just a handful of cities, sometimes even concentrated to a single data center offering services to the user. Most individual and business users are connected to this kind of service provider. An interesting phenomenon is the development of different types of wireless access alternatives. Some ISPs install access points in the public places, for example, the airports and the hotels. This gives users wireless Internet access. An IP-based router network will process IP packets containing a destination address. With the help of a routing table, the router will, at any given moment, have a roadmap helping it to know in which direction to send each packet. The packet is then passed along the optimal path or route to the destination. Simple routers often use static routing and default routes, which are quite easy to handle. Such a router has only a limited number of connections to keep track of every IP packet with an external address, which will follow a default route to the outside world. Large backbone routers, in contrast, are continuously fed with routing updates from the other routers across the Internet. This is called dynamic routing. A backbone router on the Internet will have to deal with several demanding tasks simultaneously. The router must unpack the destination address of every incoming IP packet, stall the packet while it compares the address with the routing table, then decides which outgoing interface the packet should be sent to, and then forwards it. Simultaneously, the router must update the routing table itself. Some of today's backbone routers have very large routing tables, with up to 100,000 entries. A router can be described as having two distinct paths. It contains a route processor, which handles the routing table and routing updates, and a forwarding engine, which buffers and forwards packets. In small networks, a single PC, equipped with the routing software, can easily handle both the tasks. The router does not have to know the entire path from source to destination. The only important thing for it is to keep track of the next hop. This is done with the help of routing information received from other routers and the system that can rank alternative routes. Let us take a closer look at some of the internal routing protocols. We begin with Routing Information Protocol, RIP, representing the group of distance vector protocols. Routers using RIP will exchange the routing updates containing routing tables with distances to destination addresses. The distances in Routing Internet Protocol are based on hop counts. In other words, how many routers the packet will have to pass until it reaches the destination. This is, in fact, a major disadvantage of the RIP. There is no method of differentiating between the alternative links. A transatlantic ISDN link will, for example, be preferred to a high-speed backbone link if it results in a smaller number of hops between source and destination. Due to this and other limitations, the RIP is only used on internal networks. Another common internal routing protocol is Open to Shortest Path First, OSPF, which represents the group of link state protocols. The routers using the link state protocol will exchange link states, which has statuses on different links or nodes in a network. Every router will use this information in order to update its routing table. Link state protocols provide us with some important advantages over the distance vector protocols. We are no longer limited to using hop counts as the only differentiator between alternative routes. We can also use link bandwidth and delay time over the link to calculate a ranking factor, also called metric. There is no limitation on the number of hops a route can take. As link states are immediately propagated to every router in the network, we will get fast response to the changes in the network. However, in a really large Internet working environment, a link state protocol is still inefficient. As network size increases, more and more capacity has to be put aside by the router to update the routing table. Before we establish contact with the desired host, we have to find out if it is reachable. In an IP network, this can be performed with a special software tool called Packet Internet Groper, PING. The PING simply sends out a ping packet and waits for the response. If it is up and running, the destination host will respond. We will then, as a result, get a measurement of the time it took for the packet to traverse the network to the destination. Yes, it's very much like a submarine sending out a sonar ping, waiting to receive an echo from some unidentified object in front of it. Technically, the test packet of an IP network is called an ICMP echo, where the ICMP stands for Internet Control Message Protocol. In a Windows environment, we can easily use a standard ping feature by calling up a DOS window and typing ping, followed by a web address. Ping issues 5 consecutive ping packets. The result shows us the individual round-trip times to the destination for these packets, as well as the minimum, maximum, and mean average times. One of the methods of tracing packets on the Internet is the traceroute. This application traces the packet from the source to the destination. A traceroute generates a series of pings, where the lifespan of the individual ping packet is gradually increased. The first ping will just reach the first router on its way across the network before it is dropped. A message is sent back to the originator, which tells us where it was dropped and how long it took to get there. The next packet will pass to the second router. The third packet will reach the third router, and so on. The result is a list where we can see routers which a packet has passed along its route to the destination address. We also get time measurements of how long it took to reach each router. Here, you can see the result of such a traceroute request to www.ietf.org. The requesting party is a computer connected via a dial-up modem's circuit to the network operator Telia in Stockholm, Sweden. Step by step, you can see how the ping packets pass along a series of router interfaces before a packet reaches the destination host. Notice how the destination host has a slightly different name than the web address we requested a traceroute to. An IP address can, in fact, be shared among many web servers with different names. The host will announce one name to the network, but in the domain name system, DNS, many host name entries will point at the same numerical address. Notice, too, how some individual pings early in the sequence took longer time than the subsequent ones. In most cases, this has to do with temporary network congestion in one of the routers or router links. The traceroute can tell us which network operators the packets are passing, and, in case of network congestion or outage, we can often determine where in the chain the problem is to be found. Looking at the router names, we can also tell where packets are routed geographically. Look for the example at pings 9 and 10 in the sequence. It's very likely that KBN in the router name represents Copenhagen, and NYK represents New York in some sense. Looking at round-trip times, it fits the picture well. From ping 10 onwards, the round-trip time includes a typical transatlantic delay time of somewhere between 80 and 100 milliseconds.